Now let us discuss the Cartesian spherical conversion. Let us say we have a point presented in the Cartesian coordinate system, but we want to represent the same point in the spherical system. Or we have a point in spherical coordinate system and we want to represent the point, that same point in the Cartesian. So my dear, in such cases, you must know what is the relation between Cartesian and spherical coordinate system. You know that in Cartesian coordinate system, any point is represented using three coordinate variables that are x, y and z. While the coordinates for the spherical system, they are r, theta and phi. So for switching between these coordinate system, you must know their relation. You must know how to present x, y, z in terms of r, theta, phi. Or you must know how to represent r, theta, phi in terms of x, y and z. So let us correlate them. Let us assume any point in the space as like this. And for this point, the Cartesian coordinates x, y and z can be shown as like this. X, it is the perpendicular distance from the yz plane. Y, it is the distance from the xz plane. And z, it is the perpendicular distance from the xy plane. Am I right? It's like this. And for the same point, the spherical coordinates r, theta and phi are as like this. You may remember from the spherical lecture. R, it is the distance of the given point from the origin, or it is the radius of the hypothetical sphere that is passing through the given point. Theta, it is the angle made by the r with positive z-axis, and phi, it is exactly same as we have seen in the cylindrical. The angle made by the half plane containing the required point with positive x-axis. Am I right? So this diagram contains all the coordinates from Cartesian as well as from the spherical. So from this diagram you can easily correlate now these coordinate variables. You can represent x, y and z in terms of r, theta and phi, or you can represent r, theta and phi in terms of x, y and z. Let us consider the r first. Let us find the expression for the r in terms of x, y and z. Now my dear, check out this diagram carefully. We can easily write the expression for the r by writing the Pythagoras theorem for this triangle, because r is the hypotenuse for this triangle. So we can easily write r by applying the Pythagorean theorem. Check out the other sides of this triangle. My dear, this vertical side of this triangle, this vertical side is exactly the z distance, exactly the z coordinate, because check out carefully. It is the perpendicular distance of the given point from the xy plane. So that side is z. The other side of this triangle, that one, this side can again be calculated using the Pythagoras theorem for this triangle. This side is the hypotenuse of this triangle, isn't it? So my dear, you can project the x and y distances parallelly onto the xy plane as shown in the figure, and you can write the Pythagoras theorem for this triangle to get that side as under root of x square plus y square, isn't it? So again come back to our original triangle. Now let us write the Pythagoras theorem for this triangle to get the r. For this triangle, r is the hypotenuse, vertical side is z, and that base side is root of x square plus y square. So you can easily write the Pythagoras theorem, root of side square. So you can easily get the expression for the r as shown in the figure under root of x square plus y square plus z square. Now let us consider theta. It is angle. It is the angle made by r with the positive z-axis. Am I right? And as you can clearly observe from the figure, this theta can be easily written from this triangle. So let us write its sides properly. Of course, its hypotenuse is r under root of x square plus y square plus z square. We have just seen that. Its vertical side is z and remaining side is root of x square plus y square. Just the parallel projections, as you can clearly see from the figure. So my dear, you can easily write theta from this triangle. You can either write cos theta or you can write tan theta. So if you write cos theta for this triangle, then theta formula comes out to be cos inverse of z by r, or cos inverse of z upon under root of x square plus y square plus z square. And if you write tan theta, then our formula is theta equal to tan inverse of root of x square plus y square upon z. Both of these you can see from the figure. So my dear, you can remember any one of these formula. You can either remember cos inverse or you can remember for tan inverse, whichever you like. Theta can be calculated from both of these formulas. But my dear, I would recommend you to use the formula of cos inverse z by r. Because with this cos inverse formula, with this cos formula, you don't need any extra further step. The answer written by your calculator is 100% final. You don't need any extra step. Whether z is plus or whether z is minus, whatever, in both the cases, your answer as seen on your calculator is final one. But if you calculate theta by using the formula tan inverse root of x square plus y square upon z, then the answer given by your calculator might not be correct in case of negative z. You have to take one extra step further. For example, consider the point like this. This point is below the xy plane. That means z is negative. So in that case, if you calculate theta by writing tan inverse root of x square plus y square upon z, then answer written by your calculator will be negative and its magnitude will be like this. Check out opposite upon adjacent. So answer written by your calculator is this angle with negative sign. But my dear, we always calculate theta from the positive z axis. So this is our required theta. But the answer given by the calculator for negative z case is like this. So in such cases, you have to add 180 degree to the final answer of your calculator. To get our required theta, we have to take this step. You have to add 180 degree to that answer. And that's why I am suggesting you to use cos inverse z by r formula for calculating the theta. And finally phi, it is exactly the same as we have seen in the cylindrical coordinate system. Phi coordinate is exactly same in cylindrical and spherical, isn't it? So its conversion formula is exactly the same, that is tan inverse mod of y by x, and we do changes in that formula according to the xy quadrant of the point. We have seen each and every detail for this formula in the cylindrical lecture, isn't it? So this is how we can calculate r, theta and phi of the spherical coordinate system from the x, y and z of the Cartesian coordinate system. So this is how you can convert the point in Cartesian to the spherical. Now let us find the conversion formulas from spherical to Cartesian. Let us assume that given point is represented in spherical, that means using r, theta and phi, and we want to represent the same point in Cartesian, that means using x, y and z coordinates. So we are converting the point from spherical, that means we are given with r, theta and phi as like this. Now you know that what is r, what is theta and what is phi, isn't it? But we want to represent the same point using Cartesian. That means we want the coordinates x, y and z, distances along x, y and z axis. That means we want the formulas for x in terms of r, theta, phi, y in terms of r, theta and z in terms of r, theta. Am I right? So have a look at the diagram. You can easily observe from the diagram, you can get the distances along x, y and z axis by decomposing the distance r. isn't it? So first of all, let us decompose R into its two components, R cos theta and R sin theta. R cos theta along the z-axis and R sin theta perpendicular to the z-axis in xy plane, as you can see from the figure. Now my dear, look carefully the distance R cos theta. As you can clearly observe from the figure, it is the perpendicular distance of the given point from the xy plane. It is the distance along z-axis. So my dear, according to the definition of z coordinate, it is nothing but the z coordinate. So we have got our first coordinate, that is z coordinate. So z coordinate is given as r cos of theta. Now look at the other component, r sin theta. You can easily observe from the figure, this r sin theta is in xy plane, making an angle phi with the positive x-axis. Am I right? So we can again decompose that r sin theta into two distances along x and along y as like this. R sin theta cos phi along x-axis and r sin theta sin phi along y-axis, as you can see from the figure. Now my dear, this r sin theta cos phi, it is the distance along x-axis. You can easily observe from the figure, it is the perpendicular distance of the given point from the yz plane. Am I right? So my dear, according to the definition, it is nothing but the x distance. It is the definition for x coordinate. So x coordinate is r sin theta cos phi. Similarly, you can observe r sin theta sin phi. You will come to know this is nothing but the y distance or y coordinate. So this is how any point is represented from spherical to Cartesian. We are converting from spherical, that means we know r, theta and phi, but we are representing it into the Cartesian, that means we have to calculate x, y and z. X is given as r sin theta cos phi, y is given as r sin theta sin phi and z r cos of theta. Let us solve one illustrative numerical. You can read the question from your screen. The given point is -2, 6, 3. The given point is in Cartesian coordinate system. But we want to represent the same point in the spherical coordinate system. The given point is in Cartesian, x is given as -2, y is given as 6 and z is given as 3. And as we want to represent it in the spherical, we want r, theta and phi. And my dear, we have just discussed the formulas for r, theta and phi. These are like this. So you can easily put the values of x, y and z into these respective formulas to get the values of r, theta and phi. One thing you can note that the formula for phi, we have discussed this process in the previous lectures. As x is negative and y is positive, the modification of the formula for phi is like this. So you can easily get the values of r, theta and phi, as you can see from the screen. So the given point in Cartesian is equivalently represented in the spherical as like this.